Hi all, welcome to the NPTEL online course Biophotonics and welcome to the live session. This is my session 5 and we'll wait for some people to join and we can start solving the session. Am I audible?
Yes, sir, you're audible.
Okay, we'll wait for some time such that more candidates can join.
Yeah, sure, sir.
Let us start the session and in this session,
Okay, sir.
okay, in this session we will discuss about the lasers in biophotonics. Hopefully, you people already gone through this lectures class. So I'm going to share my screen and let us discuss question by questions as well as we can go through the content along with as we are going through the questions.
Okay, sir.
Okay. My screen is visible, na?
Yes, sir.
Okay. We will go to the first question. Did you go through the content, class content of lasers?
I did till week 5, sir.
Okay. Yeah, week 5 is the lesson. Na? So,
Yeah, but week 6 lectures are also given, so I'm not studied till there.
okay, okay. No need. We can go through the lectures today of lasers, and we will go through the. Actually, we will go through the questions, and we will, from each question, we will understand the basics, and we will go through. So, this is the first question, and which we are saying which of the following phenomenon is involved in the operation of laser? And the options are stimulated emission, spontaneous emission, absorption, all of this. You want to try the answer?
I think it's stimulated emission.
Stimulated emission. The question is the which of the following phenomenon is involved in the operation of laser? Okay, so we will see how a laser will work in a normal thing. How a laser will work. Somebody want to join. So this is the first question. Which of the following phenomena is involved in the operation of the laser? So these are the answers, options given, and we will see the answers after we go through the our. So first I am going to give the diagram of a laser. So whatever the diagram, whatever a laser will have, I am going to mute. If you have some doubt, that time you can tell. So, Adarja, if you have any doubts, you can just unmute and tell. I think you can. You can unmute now whenever you want. That time you can unmute now. You just try.
Yeah,
Okay.
yeah, sir, I can.
Okay. Okay. So whenever you are speaking, you just unmute and speak. So that
Okay, sir.
yeah. So we'll go through the first thing. Actually, I'll go the diagrammatic design of a laser, and along with that one, I will tell uh, what are the things happening there. So actually, for the laser, what you want a medium. That can be anything. So I want a laser medium. So if you're having any doubt in between, you can just ask it. Hopefully, everybody is seeing the screen also. So I will have a laser medium. This is some medium. This can be anything. Can be solid or liquid or something, but this is the basic medium. Then I will have a pumping source. Just let me be my pumping source. So this is the pumping source. That also can be anything. It can be a optical based pumping. It can be electrical based pumping. It can be laser based pumping, like that. So one pumping source will be also there, and you will have. to mirror, which is called the optical resonance. One is a 100 percentage reflecting mirror, another is a little bit less than 100%. It will be like 99.99 also. This is the laser diagram. And if you see the inside portion of the active material, I am saying the if you draw the Jablonski diagram or that this transition state diagram, you can see diagram will look like something. Now I am giving the simplest form of a three-level laser. What will it will have a ground state energy level, and it will have a excited state level energy level, and it will also have a metastate energy level. So that all your electrons or the atoms are in ground state. So the atoms are in ground state. I will tell this is the ground state. Then what happens? This is the normal condition of this one. So actually I am giving a very high energy in the form of pumping. So what happens? Here I am giving some strong pumping energy. It can be like a flash lamp in the case of the first laser, like a ruby laser or something. So what happens? This started giving high energy. So what happened here? The atoms which are in the ground state will go to excited state. So actually what you are giving energy here, and with this one atoms will go to upper level. And this process is called you are giving energy and the atoms are taking the energy and going to higher level. This phenomenon is called, that phenomenon has a name. Now, yeah, if you people can unmute and tell what is the phenomenon is called, atoms are excited to higher level by taking photons or light or energy.
Light.
That process has a name.
Emission.
This emission is actually taking light and going to higher energy. That is called
Emission, sir.
emission. Emission means it should give light. It should emit light. Now this is not emitting light. Nah. This is taking light. What is called?
It's absorbing light to excite to a high state.
Yeah. So that phenomenon is called absorption.
I
So
mean absorption, sir.
yeah. So absorption is always happening there. During pumping process, what is happening there?
It pumps out the light and energy.
So absorption is happening there.
It
One of the phenomenon happening there is a absorption.
it
Okay.
releases energy.
Yeah. Now it will take energy. We are giving the energy in the form of pumping, and it will take the energy. It will go to higher energy state. So what happens? The atoms at the ground state will go to excited state. Okay. So let it be. There were like six atoms, eight atoms. Let it be eight atoms will be there. What will happen? It will go to higher energy state. All the six atom will not go to higher energy state. Okay. So if this kind of one system is there, always the chance is like atom will go, some atom will go. Let it be some four atom went to higher energy state. So in the case of a normal thing, what happens? This five atom went to higher energy state, and it will start coming back also, because it cannot stay there long time. So it will start coming back normally, spontaneously it will come with some light will be emitting. Okay, This is happening in the normal case. Any atoms which is excited to some higher energy level, it will come back. But in this case, what is the problem? It is like a normal absorption and emission, like a fluorescence kind of thing. It will absorb light and it will emit light. So it's like a normal fluorescence kind of thing will happen. Okay, there is no point of getting laser effect here. But this is a particular material. This active material is a particular material such that it can go to this metastable state. So what happens? Instead of going all the things to the ground state, most of the atom will go to metastable state, and the metastable state it can stay for a long time. That's why it is metastable. So it will stay there for a long time. So what happens? This all these five atoms will now reach in the metastable state. So it will take some time to come back to ground state. It will take some time to come back to ground state. Before it is coming back to ground state, what will happen? This is continuously pumping is happening here, na. So your light is always giving shining thing. This thing will also get excited to this place and it will come back. This thing also will excited to this place and it will come back. So what happens? After some time, number of ground state atom will be very less and the number of a metastable atom will be more. Usually, what is the condition? Usually, ground state atom will be more and higher energy state atom will be less. That's true now. In a normal atom, ground state atom will be high and higher energy state atom will be lower. But at this moment, because of the continuous pumping and because of this metastable state, atoms will come up, then it will fall to metastable state and it will stay there for some time. Again, atom will come up, go to metastable state and stay for a long time. So after some time, what will happen? The number of atoms in the metastable state will be more compared to the ground state atoms. And this condition is called the normal case where all atoms are at the ground state, less atoms are in excited state, and this distribution we can call it as the population of the atom. And at this moment, what happened? Number of atoms in the metastable state is more compared to that of the ground state. So this is something like a inverted. In the normal population, atoms at the ground state is more, atoms at excited state is less. But in the case of this condition, atoms in the ground state is less and atoms in the excited state or in the higher order state or the metastable state is more. And this condition is called population inversion. This is the inverse of a normal population. Now, what happens? Here also, atoms are in the excited state itself because there's a energy gap here. So what happens? Even though if you didn't do anything, spontaneously one atom can go down. Okay, this is called a the spontaneous coming down is called a normal. That term atoms from the higher order state is coming to lower energy state with an emission of the photon. That process is called that process we can normally is called is spontaneously happening.
Absorption, sir.
Now atom is coming to ground state and it is giving light. Now light coming out from the atom. Absorption, what happens? Light is coming and the atom is taking the light and going to excited state. Now atom is giving the light and coming to ground state. Opposite of the absorption. What is that?
Uh, Emission.
Emission,
Ah,
simulated emission.
is it stimulated emission? It is happening without anything. Automatically it is happening.
Yes, sir. Yes,
Spontaneous.
sir.
Yeah. So it is a spontaneous emission. Okay. So this also happening here. Then what happens? This is actually one of the beautiful thing of this, because all the atoms are in the metastable state. The spontaneous emission will cause one photon to come, and you see, one photon is actually in the same energy of the this energy levels, and all these atoms are at that higher energy state. So this photon will cause this atom to go down, and it will come second photon, and this also will get down, and it will cause the third photon. It will induce this one, fourth photon, induce this one, fifth photon, induce this, six, induce this, seven. Like that, what happens? Because of one photon emitted in spontaneously, that photon can trigger the other emission in the metastable state, and everything will emit at a time, and it will give a high intense pulse. That particular thing is called that also emission, but
Uh,
the
Spontaneous, sir.
emission is triggered by photon. So it is called,
Uh,
it's called,
Photon.
no, emission is triggered by photon. A photon is actually inducing the emission, and it is not a spontaneous emission. Somebody is stimulating the emission. So somebody means the photon is stimulating the emission. So it is called a stimulated emission. Okay. So in a normal laser, pumping is happening by absorption, and the normal emission is happening by spontaneous emission, and the triggered emission is happening by stimulated emission. So
Stimulated emission, sir.
it is called a stimulated emission.
Yeah.
So if you
Stimulated
see,
emission.
yeah, okay. So we can see that in a normal laser, stimulated emission is happening, spontaneous emission is happening, absorption is happening. So the correct answer will be all of these things happening. And here what will
Oh,
happen?
wow.
And here what will happen? This is actually, it is pumping. It is a atoms are in the excited state and other things. It will have a lot of atoms.
Oh, yes. Yes, sir.
Uh, this is like that way I'm saying. So lot of atoms are will be there, and it will absorb. It will go to metastable state. It will come. But what happens in the initial state of the laser? What happens? Something will emit light in this direction.
Stimulation, sir.
Yeah, some light will go this way, some light will go this way,
Yes,
some
sir.
light will go this way.
Yeah, this going this direction, sir, and the right words
Something go like this
in
way,
the present data.
something go like this way. So
Oh,
it will go at,
yeah. In this diagram, the atoms are emitting away, sir.
yeah, yeah, it will go emit at different directions. But what happens?
Oh,
So whatever the light which is gone, this direction is gone. This also gone. This also gone. These are the like
okay.
energy lost. But what happens with the photon which is emitted in this direction? It will hit in this mirror and it will come back. So it will come back through
Oh, this is
this.
the concept.
This will come back through this medium. By that time, what will happen?
Oh,
Again, this you have the pumping source. Pumping source is actually continuously giving the energy to this one. So whatever the photon is coming here, it will actually trigger the stimulated emission. But because of the stimulated emission, that will also go in the same direction. So there will be some spontaneous emission which is happening at a different direction, but the stimulated emission will be in the same direction. So the photon which is gone in the same direction will hit the another mirror and it will come back. While coming back again, these things will undergo stimulated emission. So it will go hit here, come back. Like that way, after some time what happens, light will go from one side to another side, it will hit at the mirror, from there it will come to another side, it will hit the mirror. While each pass, what will happen, the light, actually your active medium is already in the excited state. While light is passing through each pass from this side, more and more photons are getting excited and towards the what that mirror cavity side, and it is like each time the number of photon will increase and increase, and it will be like That's why it is called optical resonator. It will go hit at that side, come back, hit, come back, hit, like that it will go. And at a particular level, what happened? The intensity inside will be very high, such that this mirror cannot hold that light. So we said that this is 100% reflecting mirror, so nothing light will come this side, so there will not be any light. This is like a 99.9 percentage reflecting mirror. So what happens, the extra 1 percentage, 0.1 percentage, it cannot hold inside this one, will come at the back side of the mirror. So in like a normal light, you will see light from a transparent surface na. In the normal bulb or an LED bulb or everything, you will see light is coming from a transparent surface. But in the case of laser, you will see that light is actually coming from the backside of your mirror, where there is no, it's looking like a dark area, but after some time, the from the dark area, where high intense laser will come. And you remember that this is 99.9 percentage reflecting mirror. This 0.9 percentage only is coming out, and that 0.1 percentage is actually, we are seeing it as a very intense beam, because that very intense beam is like a 0.1 percentage of the whole intensity which is coming inside. So inside the laser cavity, actually there is a very high optical resonance is happening, and the very high intensity is happening. Only 1%, 0.1 percentage of that intensity is coming out. So this is the normal principle behind a laser. So there everything is happening. Absorption is happening. Spontaneous emission is happening. One of the spontaneous emission triggers the stimulated emission, and because of the optical tracer, optical resonator, this photons going and coming back frequently, and each pass actually the more and more photons are emitted due to stimulated emission. After some time, your mirrors cannot hold that much intensity, so actually the light which is leaking at the backside of the mirror, you are seeing it as a proper laser. Okay. Question: stimulated emission can happen between any two upper and lower energy level. Statement 2: stimulated emission is responsible for amplification and highly coherent.
Uh, both the statements are correct, sir.
Yeah. So first one, stimulated emission can happen between any two energy level. So we have different level of laser. We have 3-level laser. This is the basic level of laser. So in which what happening? This absorption is happening, then some shift happening, and this is the laser emission. So laser emission is happening in between, where metastable state and the ground state. But we have 4-level laser: ground state, excited state, some metastable state, and some intermediate state. So it can happen like a absorption is happening here, some internal conversion is happening here, lasing action is happening between 2 and 3 system, 2 and 3 levels. See, so first statement is correct. Stimulated emission can happen between any two upper and lower energy level. So that's true. Stimulated emission is responsible for the amplification of, and it is a highly coherent. So as we say this one, what happens? The stimulated emission triggers the photons to emit in the same manner of that particular photon emitted. So what happens? The coherence concept of coherence is coming there. So stimulated emission triggers the other photons to emit, and this emitted photons will be in the same phase. And what happens? it will come inside the resonance cavity, and the each time it is passing through the it is stimulated emission is happening when it is passing through the cavity, and each time the cavity is like excited due to the pumping. So what happens? So the second statement, stimulated emission is response for amplification of is highly common. That also correct. Is also correct. Statement, both statements are correct. Which are the following components of optical cavity? So actually, optical cavity contains what? Optical cavity is the place of your laser where the lasing action is taking place. So the optical cavity of the laser will contain active material. So this is true.
It will contain mirrors as well.
Yeah, it has to be excited. So pump means it's not
Oh,
normal
this was
pump.
excite atoms will give.
Yeah,
Oh,
and this will containing the
only the active is pump, sir.
what?
Only active material is only the active optical cavity, sir.
No, that is yeah. According to here, actually they said this is a active material containing as well as the pump is also containing, because that portion is the portion of a laser where the laser is coming out, and that mirror also coming. So
So the answer is all of this, sir.
uh, they given this answer is all of these. So if you have a doubt like that, because usually the cavity, when we are mentioning the cavity, what happens now? We usually mentioning the active material only.
Uh,
So I have a confusion of this question, but
the answer is
the answer which they given is like all of this. So if it is defined like that, the optical cavity is the whole cavity where that laser is produced. This whole thing will come, because the pumping material also will come, and this mirrors will also come, and the active materials also come. Okay. Why do we need a metastable state? Why do we need a metastable state?
to
All of this
Yeah, to achieve stability, to build up population inverse
and
trap.
trap the excitation energy.
So why actually why, if there is an excited state itself, why it will not, whether it will happen or not, like that way I'm saying I have two systems. One have only ground state and excited state. Another will have a same energy ground state, same excited state, and it has a metastable state. Which one I want for laser?
I would need the second one because
I
it has a
think
meta state.
Yeah, what is the requirement? Why it is a, for the two state system, whether it will be good or not?
so. What is in the second one in this?
There's an extra state here. So now you see
Okay.
in the normal distribution, the population distribution, what in the case of a normal atom, you can see this is the ground state, and as you are increasing the energy level, what happens? The population will decrease in an exponential manner. So number of atom in the ground state will be always high than that of a excited state, and this is the Boltzmann distribution law. So that you cannot do anything. This will always, that condition will be satisfied. Number of atoms in the lower energy state will be always higher than the higher energy state. So what happens? So in the case of a two-level system, so you are saying that you are giving energy and the atoms are pumped up. But what happens? The stimulated emission will also happen. The stimulated emission will trigger that So sorry, spontaneous emission will also happen, and the spontaneous emission will trigger the stimulated emission, and the atom will come down. So spontaneously also
I
atom.
mean, the answer is all of this, sir.
Yeah. So atom will come down, and as well as stimulated emission as well as spontaneous emission. So coming down will be much more higher than going up. So cannot reach a population inversion state at all. Always something is going up, something will come down. But in the case of metastable state, what happens? Whatever you pumped, it is gone up. But after that, it is not gone down. It is actually go to the metastable state. And what will happen? Metastable state, it can stay for a long time. By that time, what happens? Pumping again will happen. So after some time, what will happen? From the metastable state to the ground state, there will not be any atoms. So population inversion is achieved. So with this population inversion, what is the benefit? If something light is triggered, that will cause a racing action. Okay.
Okay, sir.
So the answer will come to achieve stability. So yeah, at the metastable state, the atoms are more stable, and it will give a stable equilibrium position for at least some time to build the population inversion, and that stability is actually giving the population inversion. Traps and holds the excitation energy. So that's also true. What happens when it is absorbing, it is getting excited, and it is falling to the metastable state. And the metastable state, what happens? The energy is actually preserved
What's the
for that.
pulse excitation energy, sir?
Yeah. So the three answer will come true. So that again your answer is all of this. What is the answer of this question? The amplified medium of a helium neon laser has an amplification spectral bandwidth band equal to 1500 megahertz at 638.8 nanometer. What must be the length of the laser cavity to ensure that only one longitudinal mode oscillates? I'm coming in 1 minute. Just you can think about the question and
0.35 meters, sir.
how it will come. You have to tell. So here actually you have to use the equation as, because they mentioned you have to. So what happens in the case of the laser cavity? There will be two mirror like this way, and this will be is the cavity length we will tell. So if you do a fabric parrot echelon equivalence to this cavity, and you can see that cavity can hold different frequencies like that way. If you check this one, the cavity can hold different mode of frequencies. What is the meaning of that one? So the laser light which is coming from this cavity containing, it will be look like some Gaussian peak, and it will containing one main mode, then another mode, and these all modes are different frequencies. And according to given equation, it is given that that frequency is like a 1500 megahertz. So in between two nearby modes have a difference of 1500 megahertz. So but what they are saying, what must be the length of the cavity to ensure only one longitudinal mode of oscillation? Only one longitudinal mode of oscillation. So, and we have the equation of this total frequency. The total frequency can be written as nu is equal to mc divided by 2 into n into L. Okay. Nu is the frequency, m will be a number, c is the velocity of light in the medium, n is the refractive index, L is the cavity length. Okay, here this is a helium neon laser. They told it's a helium neon laser. So the cavity containing only gas molecules. So it will be like gas molecules. So that gives a refractive index. We can take it as 1. And this is called the spectral band equal to the 1500 megahertz. So nu is equal to 1500. M, they put that like that way, and only one longitudinal mode of oscillation. So M will be 1. And C we already know it's the velocity of light. So we have to solve. We know that nu is equal to 1 into 3 into 10 raised to 8 divided by 2 into 1 into L, or you can say L is equal to 3 into 10 raised to 8 into divided by 2 into 1500 10 raised to 6. Okay, here 3 by 2 will be 1.5, or I can write it as 15 into 10 raised to minus 1. This 15, and this 15 is gone. This 10 raised 100 is here, into 10 raised to 6 is here. So both will become 10 raised to 8, and this is gone. Only thing which will remain will be 10 raised to minus 1 or 0.1. Okay, so the cavity length will be, so actually depends at what unit we started.
Oh. Oh, this is only the answer, 0.1.
Yeah. So you started with the answer and everything you put it in the normal, what you called SI unit only. So it will come like 0.1 meter. Okay.
Yes.
Another question. SHG of a laser light source at wavelength 1064 nanometer will occur at what is SHG? What is the full form of SHG?
Second harmonic generation.
Yeah. SHG is called the second harmonic generation. And what happens if a photon having some particular frequency is get added with the other frequency such that it will emit 2 into nu naught. So nu naught plus nu naught will add up to form 2 into nu naught. Okay. So the question is that SHG of a laser light source having wavelength of 1064 nanometer will occur at what wavelength? So the answer should be, so we know that we have the equation like C equal to nu lambda, or nu equal to C by lambda. So what happens in here? Here nu become, after the second harmonic generation, this nu, or we can write it as it's like nu zero equal to C by lambda zero. After second harmonic generation, nu will become 2 nu zero. Similarly, 2 into C by lambda. So what happens here? If 2 nu zero, if you put it as a nu nu, then this thing can be written as a 2 by lambda nu. This. So what happens in the case of a wavelength? So lambda nu will always be equal to lambda 0 by 2. So here what happens? Here the second harmonic generation is happened at 1064 nanometer. So new wavelength will be
So the answers becomes 532 nanometers, sir.
yeah. Answer will become 1064 by 2. That will be 532 nanometer. Okay. So this
Yes,
is,
sir.
so 1064 will be a infrared laser and 532 will be a green laser. So you can see that if you put a second harmonic crystal, that will be available, and if you put it in front of the infrared laser, whatever the light coming out of that what you call the second harmonic, it will be 532 and it will be green. So you will see that some invisible laser
Yes,
is
sir.
coming.
Because of the numbers I see.
Yeah.
Yes, I have a division in my mind. That's why.
Okay. Now there are two answers, two statements. Statement one: SHG is an anisotropic property. In second question two, in SHG the wavelength of the output light is half of that of the input light, and the frequency is also halved. Whether these questions are correct or wrong, or
The second is true.
second is true.
As she says.
So second is correct. And what about the first?
Oh, this only the answer.
No, no, no,
Am I
no.
right, sir?
No. I didn't complete the question.
Oh, okay, sir.
SHG is an isotropic property. So that is actually true. Okay. If the medium is isotropic, you will not get a single harmonic oscillation. So there should,
What is the reason for this, sir?
because actually this is like a non-linear phenomenon.
Oh, non-linear phenomenon
Uh,
of
so,
yeah, like emitting energy.
yeah. So if it has a isotropic property, like its a property is always in the same direction, what will happen? This what you called this that will be like a symmetric phenomenon, and whatever the components which is going in the each side will be like a opposite to the other. So but this is like a anisotropic property, which is a non-linear property, which is coming mainly because of that system does not have any symmetry, because of the
Oh, does it
ab-
have symmetry?
uh, because
Yeah.
of the absence of the symmetry. Because if you have an isotropic property, you can have a symmetry also, because that
Because of the non-isotropic property, it will not have symmetry. Am I right, sir?
yeah, so anisotropic properties actually will help not to have any symmetry there. Now the question, so the first portion is actually correct. The second one, in SH, the wavelength of the output light is halved. That is true. Of the input light, and the frequency is also halved. Now we see what is the simple harmonic, sorry, second harmonic generation. This is new zero. It will add with one of the new zero, and it will become how much? It will get two new zero. Okay. So what will be the answer? So input light and the frequency is also halved. They said this is wrong.
Both the statements are correct.
No, frequency is not half. Nah, frequency is doubled.
So the statement one is correct, whereas statement two is incorrect. So
Yeah,
answer is C. Sir.
yeah. Statement. This is a wrong statement. This is right statement. So statement 2 is incorrect and statement 1 is correct. Which of the following lasers are used in photodynamic therapy? This is a direct question from the class lecture.
Diode lasers.
Diode lasers are not used. Mainly dye lasers are used for photodynamic therapy.
Oh,
Okay. KTP lasers are like a potassium, something phosphate. That is the active materials name is the KTP. So these are actually used for our vascular treatment and other things. So KTP lasers are mainly used for this our treatment of some vascular tissues and
For
other
cancer
things.
cells.
But
Treatment for cancer cells also.
yeah, and
she says right, sir.
uh,
This is used for cancer cells.
yeah, and this dye lasers are used for this photodynamic therapy. Diode lasers are the laser which you are seeing now. Now a lot of diode laser you will see, but the commonly available diode lasers you will see in the sprinter, laser pointer, and all the this laser illuminating substances and all other things you will see this diode lasers. And CO2 lasers you will see in the industry where this laser cutting, laser welding, and this kind of things happening. They are like actually the CO2 based lasers. So here the answer is dye laser.
I mean diode laser.
Here answer is dye laser.
Oh, diode laser only.
Dye laser and diode laser are different. Okay.
Okay, sir.
Okay. Virtual energy states are imaginary unobserved states. Statement 2. the concept of virtual energy state is violates the Heisenberg's uncertainty principle, which is correct, which is wrong also.
Both the statements are incorrect, I think.
Both the statements are incorrect. What are the other?
I think statement 2 is correct because I guess it does violate Heisenberg's uncertainty principle.
Then what about statement one?
Virtual energy does violate, I guess it does violate Heisenberg's theory.
Yeah. So virtual energy states are imaginary, unobserved states. So that is also true because in the case of second harmonic generation, so what happens? The frequency at a particular frequency, it is there will be some virtual state. From there, it is add up to the another frequency, and actually it is emitting to nu naught. But we cannot detect this state at all. So we are observing the second harmonic generation. So we came up with a theory that okay, there will be some virtual state will be existed. So there will be a virtual energy state existed, and which is like a you cannot even observe or check that.
What about the
It,
statement 2, sir?
yeah, I come to the statement two. Why this virtual energy state we cannot detect it? Because these are like only came because you are seeing the second harmonic generation. Not to explain the second harmonic generation, the idea of virtual energy states they introduced, because you cannot in a theoretical level you cannot just introduce a virtual energy state there. If you put a virtual energy state there, because it will violate the quantum mechanical properties. So since it is violating the Heisenberg uncertainty principle and the quantum mechanical properties, we cannot actually theoretically predict. Because of we are getting an experimental result, we are saying that virtual energy state is exist and it is violate the Heisenberg uncertainty. So this statement is also
So I think that both the statements are correct.
yeah. So statement one is correct
As
and
you explained.
statement one,
Option A is correct, sir.
both the statements are correct.
Okay, sir.
Which of the following procedures requires an endoscope? You know what is endoscope?
Uh, X-ray of chest or either biopsy, I think.
Yeah, you see that one.
Biopsy, I think so.
Yeah, actually, you can see that thing whether since they asked that which is the following procedure requires endoscope. So they already said that which is the following procedure. So you have to see the procedure and see. Tell. So X-ray of chest. If you want to take a chest
As you said,
X-ray,
sir, biopsy is the right answer for me.
yeah. If
Okay,
you
sir. So as a biopsy, I think.
yeah, so chest X-ray does not need any insertion of endoscopy or other things, and biopsy and biopsy also not all biopsy will require endoscope. Okay, so it depends on the where the portion you are having the biopsy specimen. So but yeah, if it is like that biopsy you have to carry it out in your gut or something, you have to see what is happening there. So in order to that one, what you will do, you will give a proper thing inside your body such that you can see and take the tissues from there. So from the biopsy only you will use a endoscope, and if it is at a particular position where you can access through endoscope, otherwise there is no point of using endoscope in biopsy.
Oh, this is only the answer, I think.
Yeah, so counting by itself is
Because
not, yeah, does not require any what you call it, endoscope.
yeah, okay, sir.
Now you can tell what are the doubts you are having here, such that we can explain in a nice manner.
I have doubts in the first one, third one, and tenth one, sir.
Okay, so both of them have doubt.
Yes, sir.
No, sir, I don't have doubts currently, so you can clear his.
Okay, 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 you can tell.
How operator of laser can see three times, even though they have three options.
What?
I mean, the stimulate emission, spotted emission, absorption.
Uh, so actually, all things are happening here. This is the laser, na. So in the laser,
Now,
light is coming. So just consider it like a ruby laser. What is happening inside a ruby laser? There will be a ruby cavity, and a ruby cavity we will surround with a flash lamp. So I can show you some ruby laser diagram. Let's see. The first ruby laser, what is made, it's looking nice. I feel. So I can see the original Theodore Neyman's ruby laser. So let's see. We are seeing that. So there will be some ruby road will be here, and there will be a flash lamp which will be surrounding the ruby road, and at the end of the ruby road they are polished in such a way that there will be like a mirror.
I mean, ruby lasers are the name.
But
Am I right? Is this ruby lasers are the name of the options you discussed? Am I right, sir?
that may not be ruby laser also, but I just to give a more clarity, I just introduced the ruby laser. So you see that it will have a flash lamp. The flash lamp will give energy to the ruby road. So what happens, flash lamp will flash, it will give high intense light to the ruby road, and ruby road will absorb the whatever the energy they want. So that procedure is called pumping. So during pumping, what happens? We are externally giving some energy. It can be in the form of electricity or it can be in the form of light. We are giving the energy to the ruby road. So ruby is actually absorbing the light. So what's happening? So absorption is happening. So using that absorption, what happened? The energy is actually accumulated inside the ruby road, and from there, what is triggered? From there, it is actually started. So because of the ruby is actually metastable thing, so most of the atoms which is in the inside the ruby rod will be staying in the metastable state. So that population energy is already achieved. Then what happened, that some atoms at the metastable state can go down, and that is called spontaneous emission. Now you see that absorption happened, spontaneous emission happened. Now one can go automatically. So spontaneous emission can also happen. So if one is actually went to ground state, the emitted photon will trigger the other atoms to go to ground state and emit more and more photons. So stimulated emission is happening, and we have to get the laser light. So this is why the answer is coming like all three. So in the pumping time, absorption happens, and in the normal time stimulated emission happens, and it is triggers the laser to work. So all three things are the pumping, stimulated emission, spontaneous emission. So the answer will be your D, all of these. Now what doubt you are having?
So,
Yeah. Well, here you have doubted.
fifth one only doubts.
So this one.
Yes, sir.
So what happens? In the case of a laser, what you are seeing, so there will be optical cavity, na? So
Sir.
there will be active material, and light is coming here, coming back, coming here, coming back, and after sometimes what happens? Light is coming out. But now you see that inside here, light is going, coming back, going, coming back, going, coming back. It's coming like that. It's happening. Huh? So the light, in order to sustain inside this cavity, then it will not, like all the frequency cannot be sustained inside the cavity. Only some certain frequency will sustain. So if you look the spectrum of the light which is came inside, it will look like. So, and this all frequency or wavelength is called actually, and these are like a small frequency difference will be there, and that is called this can be called it has a term. Yeah, you can see. Yeah, so these are the frequency modes which is available for that particular cavity, and if the and your active material will have a profile, something like a Gaussian profile will have. So your laser will be a combined effect of your Gaussian profile as well as the peak. So what happens, in the case of a normal laser, it will have a spectrum something like this way. It will have a peak wavelength, and there will be like some small wavelength which is coming in the other side, and the equation of the total wavelength will be mu is equal to the wavelength mc divided by 2, and m is the number of modes, n is the refractive index, l is the cavity length, c is the velocity of the light. So if you put the equation there, you will get the length as the cavity length. Okay, Any doubt in that one?
This V equal to 1 into 3 into 10 power 8. That's only 2 by 2 into 1 into. How did they came, sir?
Which one?
That V1.
This one, na? So M is the one which they already told that only one mode is present there.
Oh, that's the created as sub like 1 into 3 into 10 power 8. Am I right, sir?
Yeah, yeah. 1 into 3 into 10 power 8 is actually the c. M is 1. C is the velocity of light. 3 into 10 raised to 8.
What's the C value?
C is the velocity of light, na? 3 into 10 raised to 8 meter per second. Okay. So if we substitute that one, we will get the answer as 0.1 meter. Next,
How did the 0.1 meter value came?
that you solve, na? This thing you understood, na? 1 into 3 into 10 raised to 8 paid by 2 into this equation.
Um, Not much.
But yeah, actually you don't need to derive that equation. But this will be actually derivation of that equation. You have to see how small wavelength is actually combines to form constructive interference and destructive interference. Then you will have a condition that okay, this is the condition for constructive interference. Then only if the constructive for interference happened, only the what you call it, yeah, that optical cavity can sustain the light inside the cavity. So by putting the equation, actually you will arrive with this equation. Mu is equal to mc divided by 2 n lambda. M is actually 1, c is actually 1, sorry, c is actually 3 into 10 raised to 8, 2 into n is actually 1 we have to take, because the medium is a gas medium, and the helium neon mixture is not a gas which will be like which has a more than higher refractive index. So just since it's a helium neon laser and it's a gas medium, you can take the what do you call it, refractive index as a 1, like in normal air itself. And L is the one which we have to calculate. So if you do the calculation, you will get a 0.1 as length.
Okay.
And ask question. What are the other doubts?
Yes. What about the counting platelets in this answer?
What?
I mean the counting platelets.
Didn't get. What?
In the 10th question, what is the answer here for counting platelets?
I'm not hearing.
Um, in this question,
Yes.
there are three options:
Ah,
X-ray of chest, biopsy, counting platelets.
okay. What is the procedure for counting platelets? Okay. Counting platelets are actually happened. Now there are some blood counting machine itself is I think available. It is not using endoscopy at all.
Because it's a blood related
Yeah,
subject,
yeah.
I
So
think.
lasers are not used. Maybe laser may be using for in the along with some microscopy and other thing, but it is not like endoscopy because endoscopy is actually used with this optical fiber plus some light source. So that which is not at
So,
all required for a platelet count.
oh, these two X-ray of just counting of
No, no,
platelets
no, no, no,
only.
no. X-ray of chest I just marked because of this told. So X-ray of chest is
Oh,
wrong answer. Only biopsy is the correct answer.
uh, what are the reasons for this biopsy used in endoscope?
Yeah, that I'm saying. Bio. You cannot say that for all biopsy endoscope is needed. That depends on the biopsy is the technique of taking tissue and analyzing that one from a living body. From the living body, you will take a
So, what is the application of biopsy, sir?
biopsy is actually used for mainly biopsy is used for diagnosing cancer. So biopsy, what they will do, this cancerous cells, they want to check that whether the cells have the enormous growing capacity. Because if the cell is a cancerous cell, that will grow, consuming almost all the nutrients which is coming to your body, and it will grow very fast, and it will make the other tissues grow very slow. So as a result, your body, our body will become very weak as well as this growth of that kind of cells will cause some tumor and other things. So if
Other
that
than cancer's identification,
that
I
will
mean,
be
other than this.
different thing will be there. Like scans are there, like a CT scan, MRI scan, kind of things are taking for identification. But this biopsy actually whatever we want is like a endoscopic thing. So that will be like a if the biopsy has to be carried out inside the gut or something inside our what you call
Oh, this is also used in guts
ah
and
no,
gallbladders, thing
ah
something.
yes, but yeah, wherever your fiber has to reach the now think that some what there is some tumor on the upper part of the skin. You have to do biopsy. The doctor will remove the tumor and they will send it for a checking. But in that case, nobody is going to use endoscope because with your naked eye, if you can see some things, then what is the need of putting one endoscope there? So endoscope is actually used to see the proper images, which is actually
But
unacceptable to
in this,
us. Uh,
uh, I studied the concept biopsy in surgery and microbiology subject
uh,
in my BME group, our BME group. Sorry.
uh. So that is the thing
Due to
which is
I thinking, I have an idea of the concept, sir.
yeah. So you don't need a. So depends on where the biopsy is carried out. You can use endoscopy or not. So if it is something like peripheral places, you don't need to use a endoscopy at all with the biopsy.
Yes, sir.
So the doubts.
No doubts.
Is any part other than this part whether you have to clarify something that also you can tell now, such that
And no need, sir.
So is it clear? Everything is clear for you people?